Hello all. I'm really excited to be here with all of you in Las Vegas today. Hope you all caught Thomas and Amin's keynote earlier this morning and heard some of the exciting things we are working on at Google in the AI space. My name is Sudhakar Sannakkayala, and I lead the AI compute engineering organization at Google Cloud, including both GPUs and TPUs. Today, I'll be joined by Artur Rodrigues, a member of the technical staff at Anthropic, one of the major AI labs running their workloads on Google's cloud. I'll spend the next 15 to 20 minutes detailing Google's specialized TPU infrastructure and how it drives innovation for our advanced AI customers. I will focus on the latest breakthroughs in delivering maximum performance, scale, and reliability for the world's most complex workloads. Artur will deep dive on how Anthropic leverages these infrastructure breakthroughs to develop and scale the next generation of Claude models that serve tens of millions of users worldwide. For those of you unfamiliar with TPUs, tensor processing units are Google's custom-designed ASIC, specially engineered to deliver the industry-leading absolute performance with best-in-class cost and power efficiencies at the massive scale required by today's AI workloads. While TPUs have been the foundation of Google's internal AI innovation, we've made them generally available through our AI hypercomputer architecture on Google Cloud. This architecture offers a choice of orchestration and cluster management, flexible consumption models, support for popular frameworks like PyTorch and JAX, and performance-optimized hardware, including compute with TPU and GPUs, storage, and networking. So TPUs work with multiple components of the AI hypercomputer stack to deliver high performance, reliability, and scale for our customers. Since 2015, when Google launched the first version of TPU, with every TPU generation, we've made the TPUs faster, more scalable, and very efficient. Some of these improvements include introducing the ICI domain, the 3D torus topology, liquid cooling, integration with the AI hypercomputer stack, and support for lower precision numerics. Speaking of improvements, today we announced our 8th generation of TPUs, TPU 8T, purpose-built for large-scale training, and TPUs 8I, purpose-built for reinforced learning and low-latency serving. Throughout my talk today, I will highlight some of the forward-looking advancements in these 8th generation TPUs. Now, throughout our journey in the last 10 years, we've focused on engineering infrastructure solutions that serve a wide variety of AI customer segments. Our TPU customers range from AI labs and researchers scaling massive foundational models to digital natives and enterprises building cost-efficient inference applications. So by deeply working with these customers and understanding their workloads, we've co-designed our hardware and software infrastructure stack to meet the specific requirements of these customers in these various user segments. Due to the heterogeneity of our TPU customers, our engineering efforts have been primarily focused on 4 key pillars. First, performance that's focused on throughput, latency, and maximizing scale. Second, in a reliable and resilient manner at planetary scale. We've also invested heavily in ensuring flexibility that iterative AI development requires while making it easy to adopt and use TPUs. While all these 4 areas are important, AI labs like Anthropic are truly pushing the boundaries of innovation, especially in performance and reliability and resilience at scale. I will later highlight, actually, That's the majority of the talk will focus on performance and resiliency at scale. I will later highlight some of the other sessions happening later this week that will focus on flexibility and ease of use of TPUs. As we're all aware, delivering maximum performance per dollar is paramount for any AI infrastructure. To truly understand the TPU's unique value, let's examine how TPUs drive absolute performance across the distinct segments of the foundational model lifecycle. The journey of building a frontier model is a continuous cycle of model and infrastructure optimization. It breaks down into 3 distinct stages. First, pre-training, where a massive generalized base model, which is the foundation of a model like Claude, is created by processing vast amounts of data. The second stage is post-training, where the model uses supervised fine-tuning and reinforced learning and gets refined with human intent and safety. The final phase is inference, where serving models with low latency for real-time applications or batch inference, which Anthropic leverages for their applications like Claude Code and Claude Cowork. Now, let's first take a look at the pre-training phase. The TPU ASIC achieves high throughput training by utilizing a systolic array architecture. This architecture helps remove on-chip data bottlenecks by streaming data across thousands of interconnected chips for matrix multiplications for dense computations. Think of this as an assembly line for matrix multiplication. Also, the TPU architecture supports specialized sparse cores to accelerate embedding heavy workloads and non-matrix multiplication operations. TPUs also support low-precision numerics like BF16 and FP8. Looking ahead, with our 8th generation of TPUs, we'll offer support for FP4 natively. Now, lower precision numerics helps pre-training performance by reducing the computation and data footprint, lowering the energy consumption, and all of this without compromising on your model quality. Now, to further maximize performance at the pre-training stage, these high-powered chips are connected to each other through our proprietary ICI topology network within a single ICI domain. Think of the TPU ICI domain as NVIDIA's NVLink GPU domain. We at Google call it as the TPU pod. Now, our 7th generation of TPUs, Ironwood, have 9,216 chips that are interconnected with 1.2 terabytes per second bidirectional bandwidth, capable of handling the world's largest workloads. These pods are interconnected by 6 links per chip to form a 3D torus topology. Our largest TPU pods are comprised of cubes of 64 chips that are connected to the nearest neighbor through optical wraparound links. These cubes are reconfigurable to connect to each other for much larger topologies or shrink down and break down to smaller topologies based on the needs of your workloads. Now, with TPU 8T that we announced today, our ICI domain will scale up to 9,600 interconnected chips. Now, for large frontier model builders, we need to go beyond a single pod into tens and thousands of chip scale. We support this in our TPU infrastructure through a concept called Slice. Slice allows you to configure jobs to tens of thousands of chips, leveraging the ICI domain and also your data center network. Now, to extract maximum scale and efficiency, we support several sophisticated parallelization and compiler strategies to enable multi-slice training across ICI domains to build a single large training cluster that has tens of thousands of chips. Now, when you train frontier models, scale is everything. This is where TPU architecture truly shines. The TPU Ironwood ICI domain is 16 times larger than the next available accelerator domain in the market. And with multi-slice capability, clusters can scale up to 600,000 TPU chips, truly world-class. For pre-training, in addition to the hardware and infra capabilities, let me touch on the additional hardware and software optimization that truly differentiate TPUs for large-scale pre-training. The TPU hardware and software stack provide a number of kernel optimizations, model and data parallelism, offloading, scale capabilities that allow customers to get maximum performance and at this scale. As I mentioned, TPU has also this sparse core capability that gives you a way to offload non-critical computations. So this allows the main TPUs to entirely focus on the critical tasks, leading to vast performance gains. Our leading model builders consistently realize remarkable efficiency, reaching high machine flops utilization of up to 80% to maximize every cycle of compute. Our architecture also provides a massive 1.8 petabytes of shared HBM on our 7th generation Ironwood TPU architecture. And even at this gigantic scale, our infrastructure maintains an impressive 68% MFU and up to 97% good put for pre-training. Now, once the model is trained, we enter the critical post-training phase. This is where the model learns critical capabilities such as reasoning, math, coding, agentic tool use, safety, and alignment with real-world applications. Supervised fine-tuning, especially reinforced learning, is a capability that has driven massive model performance gains lately for our leading labs. TPUs enhance post-training performance through a variety of specialized hardware and software co-design optimizations, like agentic RL fine-tuning, supervised fine-tuning, distillation, and support for popular reinforced learning algorithms. Again, this is where the TPU architecture truly shines. Based on the RL technique employed by our model builders, the systolic array design, the matrix multiplication units, the sparse core capability, the large ICI domains in HBM, and support for lower precision numerics truly shine to enable maximum performance at the post-training phase. Now, let's shift from post-training to inference, which is the final stage. And let's examine how specifically TPUs support large-scale models across billions of customers worldwide. TPUs support popular open-source inference engines like VLLM and SGLang, and offer very competitive price performance while running these inference engines on our TPU architecture. VLLM is supported with our 6th generation of TPUs, Trillium, that is broadly available for you globally. Also, our customers can serve the same model both on GPUs and TPUs using our custom compute classes. In this way, our customers can choose the best accelerator for the job for the right model. TPU architecture also ensures near zero developer friction and minimal workload disruption while running VLLM on our TPU architecture. You can retain the same VLLM interface that developers love, and you can switch your existing inference deployments to leverage TPUs with few minimal configuration changes. With the inference innovations that we are announcing at Next, I'm thrilled to share that with DWS consumption mode on TPUs, you can achieve over 2 times better performance on our TPU architecture versus our comparable accelerators. To supplement our infrastructure capabilities, let me touch on a few differentiated hardware and software optimizations that the TPUs offer. First, continuous batching. Instead of waiting for a batch of inference requests to arrive and process, TPUs process requests as they come in, thus reducing latency and time for first token. Weights quantization allows you to reduce model size, decrease HBM and bandwidth requirements. KV cache quantization allows for larger batch sizes, longer context windows, and being able to hold larger models in the TPU memory HBM. Paged attention is another technique. Traditional attention mechanism uses contiguous memory. Paged attention partitions the KV cache into blocks, resulting in less memory fragmentation. This enables for high throughput for your latency, for high throughput for your inference applications, sometimes even 2 to 3 times faster. These techniques, often used in combination, allow TPU-based inference servers like VLLM on cloud TPUs achieve lower latencies, higher throughput, and better hardware utilization. In addition to these techniques, we support techniques like disaggregated serving for independent scaling of the prefill and the decode phase for ultra-low latency serving. You can observe over 7 times faster time to first token and 3 times faster time per output token when you move to multi-host disaggregated serving from single-host interleaved serving. Now, the ability to scale near linear performance needs to be supplemented by an end-to-end software stack that's co-designed to offer high flexibility and ease of use. TPUs drive ease of use and flexibility through an open, modular, multi-framework software, which is co-designed with the hardware. The TPU stack features the XLA compiler and distributed runtime, including pathways, working in harmony with the TPU hardware. We provide broad framework support, including JAX that powers Gemini and PyTorch on TPUs natively. We've simplified workload orchestration with tools like GKE and Ray. To further improve usability, we provide solutions like MaxText for pre- and post-staining and high-performance inference engines like VLLM and SGLang, as I mentioned. Ease of use is further improved on our TPU architecture with dynamic workload scheduling and CUDs. And all of this architecture is supported by a simple day 0, day 1, and day 2 experience that's backed by robust monitoring, diagnostics, and debuggability for our customers. While performance is always key, the infrastructure needs to deliver performance at a highly reliable way that is resilient to failures. Given the budgets spent by our AI labs on AI infrastructure, we want to ensure that their infrastructure spends more time helping them with their innovation rather than being blocked by infrastructure failures. With Google's TPU innovations, we've observed that compared to the next accelerator, TPUs deliver 20% more goodput at a large scale of 128K chip scale, which results in faster time to market in launching the next generation of frontier models. For builders of large frontier models who are always pushing the boundaries of the AI infrastructure, while performance is important, so is reliability at scale. A single hardware failure can jeopardize a multi-month training run, and the associated millions of dollars of investment that goes along with it. And to speak more on how Anthropic is pushing the boundaries of TPU reliability, resilience, and scale, and leveraging everything we talked about today, I would like to introduce Artur Rodrigues. Artur is a member of the technical staff at Anthropic. He builds and scales the infrastructure powering the development of the frontier Claude models. Welcome, Artur.
Thank you, Sudhakar. Good morning, everyone. Thank you for joining this talk. I'll apologize in advance for my rough voice. I'll try my best to keep it clear for you folks, but I developed a sore throat. Thank you very much for joining us this morning. As Sudhakar said, Anthropic and Google have been collaborating for a few years. And as a member of the infrastructure team at Anthropic, it's my job to make sure that the rest of the company has access to highly available compute infrastructure. And today we're going to focus on Google TPUs. So the story, at least from my perspective, begins in 2024 when we got access to the first large fleet of TPU v5 capacity. This capacity was primarily non-elastic, and as I'm going to dive deep here, it required us to build some amount of automation behind the scenes to make sure, again, that it was highly available to the rest of the company. In here, for these slides, I'm going to focus on both for V5s on the 2D topologies, but also on the 3D ones. The V5s, as I mentioned, was our first large footprint. And Anthropic is in a very specific position, as Sudhakar mentioned, as a large model builder, that we know exactly how many chips we're buying from Google and how much we have access to. This might be different from smaller customers that kind of spin up compute on demand, but we know how much compute we have. So traditionally, if you want to have access to these TPUs, you provision them in a specific topology. Internally at Anthropic, we call this hard slicing. So we tell exactly Google, hey, I want a 16 by 16 TPU v5v capacity, or I want a 4 by 4 by 4 TPU v5p capacity. And that goes over, we use Kubernetes, that goes over GKE. It is provisioned as a node pool to us that we can then use internally. You pick the topology, and it's presented to you specifically on that shape. However, things change over time. Maybe you've built a model and now it's time to serve, as Sudhakar was mentioning. And at that point, you might need to change what was before a 16 by 16 into a combination of smaller topologies. So you might want, for example, to convert a 16 by 16 into 4 8 by 8s, or to convert a 4 by 4 by 4 in a bunch of 2 by 2 by 2s. Traditionally, back in 2024, if we had to do this, again, it would involve deleting those node pools and recreating them as smaller topologies. The downside of that is that while it's kind of flexible and we had good APIs, is that there's a time component involved in there, around 10 to 15, and in some cases 30 minutes to get that capacity back. And that time eats into kind of the availability numbers that my team is responsible for the rest of the company. That's why we ended up kind of developing what we call the maximizer internally back in 2024. So here I'm describing what kind of a few 16 by 16s would have looked like internally. At the top left, you can see a fully healthy 16 by 16. Again, all of these are physically 16 by 16s in the Google data center. In the right, you can see that we have an 8 by 8 that potentially has failed because one of the hosts went bad or one of the links went bad. And in the other bottom ones, you can see that we've provisioned that capacity as different topologies. And you can even see one here in the top, in the bottom right, where we have a host that's specifically unhealthy and we cannot provision. So we've developed this model, this maximizer component, a piece of automation that basically tries to spin up as much capacity as possible, given the constraints that we kind of have to work with. So the first step here that we go through is to clean up the unhealthy host. So that 8 by 8 that at one point was healthy, it became unhealthy, we have to clean that up. So we clean that up. Then we go over a series of steps to try to provision bigger topologies and then moving on to smaller ones. So as you can see at the bottom, what was before a bunch of smaller topologies, but we have fully healthy hosts, we can now, through a process called priority boost, provision them as a fully healthy 16 by 16. So now we have two 16 by 16s, which in most cases for us, it's a net benefit. Then, as I mentioned, we're going to go over those smaller topologies. So from a 16 by 16, we then move into an 8 by 16, and so on and so forth. basically trying to fill in the blanks within the capacity that we kind of have bought or have acquired and committed to with Google. So we do this multiple times over the day or over the week, depending on how many unhealthy hosts we have. And that was basically the way that we had to kind of tap into all of the capacity that we bought. The old repairing hosts, they can also become healthy. They can become healthy, and then we would potentially be able to convert what was once a bunch of smaller topologies back into a 16 by 16. Then, later into 2024, we were able to co-develop with Google, and my talk is all about kind of co-developing and kind of pushing the frontier of what the first-party features are available, what we call sub-slicing, which is basically the ability to no longer have to pay for the node pool deletions and instead keep our 16 by 16s as it is, and at scheduling time, sub-slice it into different ones. So again, instead of like doing the hard slicing and deleting the node pools, we're now able to the manipulation of some of the JAX environment variables to use that 16 by 16 as different topologies. And this is a huge win for us in terms of availability, because we don't have to pay the price, once again, of the full node pool reprovision. It's important to stress here that this was a feature that we co-developed with Google, and because we have our own scheduler, we are making the decisions on which workloads to evict and change that 16 by 16 into different topologies as needed by our internal demands. And once again, this could be from potentially an inference job that now it's going to be replaced by a bunch of research jobs, or a training job that's being replaced by a bunch of inference jobs. Then 2025 came, and with it came the V6E family of TPUs, and a bunch of new features were introduced. The first one of these that I want to call out is what Google calls restarting place. As you previously saw, we can have, in a 16 by 16, suddenly a subset of the hosts go bad. Before, if that happened, we were forced to do what we call the deletion of the node pool, pay again for that provisioning time, and have to fill in the blanks again, either through manually or through the maximizer process that I described, into the smaller topologies. But now with sub-slicing, what we can then do is keep that 16 by 16 as it is, send that host to repair internally at Google, and still use the 16 by 16 through smaller topologies. This, again, driving the availability cost because we don't have to delete that node pool and create smaller ones around and then back again. Once that host is back healthy and back from repair, we can then use the 16 by 16 as a fully healthy slice again. Again, bringing kind of higher levels of availability for the rest of the infrastructure. The other feature that landed in 2025 that was quite interesting for us, especially from an accounting perspective, was the ability to have stable hardware identifiers. Traditionally, if you delete a node pool, even knowing that the underlying hardware is the same, you would be exposed to different IDs. So let's say that you have a 16 by 16, you delete it, you recreate it, you delete it. That host is presented as a different set of IDs. For most cases, this is not a big deal, and it doesn't really change things. But at the scale that Anthropic operates on, we're actually interested in knowing which one are the hosts that we're seeing for the first times, which one are the ones that just came back from repair, because we then might be interested in doing, for example, some types of burn-in or build higher confidence that that hardware is good. And instead of like dedicating it, for example, for a research workload, we might want it in a production training run. So we're able to kind of track the life cycle of the components individually. And this level of visibility is actually really, really nice and something that we're really happy to partner with Google in the past to have access to. In this specific case that I'm showing, we might have sent the host for repair, and the host itself, so the compute tray, might have been fine, and the problem was in the TPU. Then we can see that the TPU chip IDs would have been replaced, and the host stayed the same. And that goes into our ledger in the way that we account for this capacity. The other thing that arrived, and that was actually quite important for the sub-slicing that I just presented, is the fixed host coordinates. Before, to achieve the sub-slicing that I just described, after ingesting a 16 by 16 for the first time, we would have to run a specific JAX program that would map that 16 by 16 into specific coordinates so that we knew exactly where each one of the hosts were. And based on those coordinates, that's how our scheduler was able to say, okay, this 4 by 8, it goes on exactly this position, or this 8 by 8 on the exact one. But then in 2025, Google shipped that as a first party kind of feature. And once the hosts were provisioned through GKE, we would have the exact what was called a partition tree for those hosts. So again, we were saving this extra component, this extra piece of infrastructure, something that would take like between 10 to 20 minutes, just came for free as like node labels as part of GKE. And our scheduler is just able to use that to place workloads exactly where they needed to be. One of the nice things, at least for me, who is an infrastructure engineer, was their ability to kind of build what we call a kind of a fleet hardware map. So when I'm bored, I like kind of going into our dashboards and like walking over kind of our data center that actually lives in a Google data center. And before that, what we actually had to do was basically map out through Kubernetes these node pools. And if I had a 4x4 node pool that was hard sliced, I actually didn't know which exact kind of rack it was a part of inside of a Google data center. So I would have like these smaller node pools kind of in my hardware map, completely isolated. But then, thanks to these specific hardware identifiers, what we're able to then do together with the new coordinates was know exactly what are the pieces of hardware that we have in Google and map those out. So that same kind of picture that I showed before, it would actually translate into something like this. In red, these are, for example, hosts that I have seen before but that have gone into repair. And in the kind of bottom right one, these white marks are hosts that I've never been able to provision, for whatever reason that might be. But it just allows us to actually build a physical map of the data centers from Google. And again, this is an unprecedented level of visibility that really allows us to scale the infrastructure with very high confidence. This gets us to 2026 with the V7X family that started rolling into production earlier this year. And this brought, yet again, a bunch of new features that drive up visibility and availability internally. The first one of those is what is called incremental provisioning. So before, as I mentioned, if there was a hardware that was bad specifically, we were never able to kind of provision that as a 16x16 or a 4x4x4. We were forced to wait through that maximizer process up until that underlying hardware was fully healthy to bring it back as a 16x16. Now with incremental provisioning, what we're able to do is say, I want this 4x4x4 in this new specific mode. And what actually happens is that I actually get that 4x4x4. It won't be fully healthy yet because Google is repairing that hardware, but I have that kind of physical hardware expressed at the exact same topology that exists physically. And once that kind of capacity is healed and fixed, it is reflected automatically through GKE node health status. And we can use it as a fully healthy 4x4x4. So hopefully at this point, you're starting to kind of see how each one of those features build on top of each other. And the ones that I've been expressing with sub-slicing, then moving into specifically kind of this host coming back healthy and incremental provisioning, that the job that I'm having to do or the automation that I'm having to build to kind of use that capacity to the maximum level is diminishing. So this is a talk that like hopefully is showing how we're kind of co-developing and bringing these what were once specific features that we developed internally into first-party features. This moves into kind of dynamic slicing, which is the ability to kind of build big slices using that kind of really big ICI domain that Sudhakar just outlined for the V7X family, which goes up to 9,216 chips. At Anthropic, as I mentioned, we have our own scheduler. And my previous year's talks, for folks who are interested, I go in a little bit more detail on what that scheduler looks like. But we've been investing in a custom scheduler because we have specific requirements around topology, around how we gang schedule our workloads. So I'm going to give a sneak peek into how we've been using these new features to actually build these slices at runtime through dynamic slicing. So in here, we have two 4x4x4 cubes, and they've been provisioned in what is called the provision-only mode. So some of the ICI links here have not been activated. So I just have the physical hardware expressed as a node pool in our clusters. A new job comes in. This might have been from a researcher, or this might be an inference kind of workload that just arrived. And it is requiring a 4x4x8 in this specific case. Let's assume for now that these cubes, they are spares, and they're not being used by any other workloads for the sake of simplicity. Our scheduler is going to notice that these cubes are free and that they can be used and they can form a 4x4x8. Again, together with OCS and this dynamic slicing, I can join any cube within that pod, regardless of where they are, thanks to OCS. it is going to bind those pods into those nodes. We've developed a new component called Slice Manager that sees that we have bound pods that don't yet have a slice, and it will then create this new slice CR that was introduced in the V7X family that is part of the dynamic slicing. In here, you can see that we have the specific partition IDs that need to be used. So we, Anthropic, are telling Google specifically, I want to control the OCS links in this specific way. I want these cubes joined together to form a 4x4x8. This is a level of control that, again, is unprecedented and that we didn't have before in the same SCI domain. So Slice Manager creates that slice, and a Google internal component that's expressed in GKE, but also internally called Slice Controller, will observe that there is a slice intent, and it will actually control the OCS in the data center to form that ICI domain. It will eventually become ready, and we can observe it because that is reflected back into this slice CR within Kubernetes, and our workload can begin, and the JAX initialization will take place. Once the job is complete, we can simply delete it, and that slice is now orphaned. And it's up to us, again, to delete that slice and reuse those cubes that are now spares in whatever way we want. And here, this is just an example with 2 cubes, but hopefully you can start mapping on how like having different levels of topologies can be formed together to make use of the full pod ultimately. This allows us to move actually into a little bit of failures and new features expressed as well in the V7X family and Cluster Director, which is a new feature that was introduced this year. And here specifically about link visibility. So we have a 16x16 just to make it easier to see as opposed to a 3D topology. Let's assume that we have a link failure, a true link failures in this 16x16. Previously, without Cluster Director and a slice CR, we would be forced to make sub-optimal utilization of that 16x16 because we do not know exactly how that link failed. So we have to assume the worst case scenario without the slice CR and without Cluster Director. So we have to assume that it could have been either the link or the 2 hosts that participated in it. So what was once before a 16x16, now I can only make use of it in this configuration that I'm showing to some degree. You can fill in the smaller ones, but here for the example, those 4 hosts cannot be used. However, with Cluster Director, we have visibility into exactly what has failed in those hosts, and we can know, for example, that the hosts are healthy, and it's just the link that has failed. So it allows us to kind of make use of a bigger topology domain in that same 16x16. So as opposed to kind of having at most an 8x8 as a largest topology, we cannot have an 8x16, but also 2 8x8s and fully utilize the hosts, albeit not fully the ICI links. Another thing that's kind of can be used with the V7X family is ICI's resilience routing. So here, I'm zooming in at the chip level and not the full kind of 16x16 or a full kind of cube. But let's say that we need comms to happen between kind of these 2 chips that are highlighted as source and destination. One of the links fails. Traditionally, if you're not opting for resilient routing, the normal routing that would take place is now failed, and you wouldn't be able to use it. However, if you opt in for what's called wild first routing, the routing can now take place to kind of healthy links, and your workload can continue to run, albeit at a lower performance level. But you don't necessarily need to kind of stop the workload or like fill the workload entirely. You can continue up to the next checkpoint or up to completion depending on how you want. Again, flexibility for our workloads, which what was once before required us to kind of tear down the whole workload. The new feature that was introduced in the V7X family is what we called kind of cube hot swap. For this example, let's assume that we have 4 cubes joined as a dynamic super slice, here shown by these 4 partitions, which are the cubes themselves. And now let's simulate that one of the hosts in one of these cubes failed. Traditionally, what we would have been forced to do was to tear down the whole node pool because you have expressed that as a node pool, not as a slice in a slice CR with the V7X family. All of the pods would have to be deleted, rescheduled, a new node pool created. But in here, because we're using dynamic slicing, what we can actually do is have Slice Manager delete the slice while keeping the pods that are on healthy cubes running, create a new slice that's now targeting a spare cube that was fully healthy, because we know it was, because again, we have that level of visibility in Cluster Director. We form a slice, bind only new pods to that specific subset that has failed, so this one cube D here at the bottom right, and then restore from a checkpoint. So what was once before perhaps a 1 hour kind of downtime, now it can be as fast as a few minutes through this hot swapping capability with V7X and Cluster Director. So to kind of summarize and leading up to kind of what was hopefully kind of this journey together with Google to have bring higher levels of availability and visibility as first-party features. In terms of failures, you can have a link failure, and you can absorb that failure through first routing. You have a perf RIT, but the workload keeps running. If a cube goes down because of a host went down, for example, you can do a hot swap of that spare cube and do the OCS rewiring through slice CRs. It's having to take the snapshot restore. And if by any chance you're already using the full pod because you're kind of literally using 144 cubes, you're then forced to reschedule and downsize your workload, but that's still an option. And if we were to kind of zoom in into this V7X kind of pod level of scale, which again is 9,216 chips, and if we go over the families over the 3 years, this is how I like to see it. In V5P, we actually have to go through DCN, so it's almost a 2x kind of scale up from what V5P had, and I would have to join 2 of these pods over DCN. And if there was a failure back then, I would actually have to replace a whole slice, half of that. Again, recreating that node pool, and it would join as a new DCN peer. With V5E and V6E, that goes over the mega scale functionality from JAX. And again, the inter-slice links are over DCN. And if something fails, I have to replace a full 16 by 16. You have to have that one node pool healthy and as a spare if one of them fails. And again, it joins as a DCN peer. This year with V7X, we have one single ICI domain with 144 cubes. And there's no kind of DCN between them. It's fully ICI, as I just said. That level of performance that Sudhakar just underlined a few minutes ago. If there's a failure, I replace a single cube, so 64 chips. And the spare that I'm keeping warm is one spare cube. And it's going to join the same ICI domain, so there's no DCN involved. And here to finish off, this is how we've been seeing how TPUs have been rising and how we've been co-developing with Google over the past year. We have computational requirements, and kind of the scale keeps getting bigger in this ICI domain. As we said, unprecedented levels of bandwidth with the V7X family. Still having the ability to do mega scale and multi-slice jobs to kind of use multiple pods at the frontier scale. At the hardware level and resiliency and the ability to tolerate interruptions, we have hot swaps, we have the ability to use these ICI resiliencies and still kind of restore from a checkpoint. And the observability is also unprecedented with Cluster Director, the stable host IDs, and the ICI link visibilities that I just described, while also being extremely flexible to control the Google data center from our side of the table. So yeah, wrapping up, hopefully by now you have seen that together with Google, my job is becoming easier because there are fewer hacks or fewer automations that I'm having to build, and I'm actually starting to unwind some of those things. And I'd like to invite Sudhakar back in the screen to wrap this up.
Thank you, Artur. Before we conclude, let's quickly recap the key takeaways for today's talk. First, TPUs offer the performance that most demanding AI workloads require. Second, our automated fault recovery and intelligent scheduling that Artur spoke about are designed to maintain continuous uptime even across massive pod scale deployments. And finally, this is why AI labs like Anthropic are using our TPU infrastructure for the most advanced frontier models in the world. Now, before you leave, I hope we've been able to show you how TPUs are designed to push the boundaries of AI innovation. I would highly encourage you to attend the following sessions from my team. Breakout session 171 to get a closer look at our cloud TPU overall roadmap for the next couple of years. BRK 175 for the cloud TPU experience. It'll mostly cover the flexibility and ease of use pieces that I spoke about earlier briefly. And finally, breakout 69 that purely focuses on inference on TPUs. I highly encourage you to check out these sessions. Also visit the AI hardware booth on the Explore floor. You can get to check out a full TPU rack. And also, we might have some chips on display that you can hold and see as well. And also visit the TPU website for more information. Thank you again. Thank you for visiting this talk. If you have any feedback, please let us know. Thank you so much.